The tight binding model. A first principles route to band structure in solids. An isolated atom has discrete bound states, with wave functions that decay exponentially away from the nucleus. When identical atoms are assembled into a periodic crystal, these atomic orbitals on neighboring sites begin to overlap. The overlap generates off-diagonal matrix elements of the Hamiltonian between sites, and these matrix elements are precisely what allow an electron to delocalize across the lattice. The tight binding model is the systematic framework that exploits this picture. We assume the atomic orbitals remain a good local basis, retain the intersite couplings as the only off-diagonal terms in this truncated basis, and from this minimal input, we will derive the full electronic band structure. Our starting point is the linear combination of atomic orbitals, or LCAO. The crystal Hamiltonian commutes with the lattice translation operator, so its eigenstates can be chosen to simultaneously diagonalize translations. This is Bloch's theorem, and it labels each eigenstate by a crystal momentum k lying in the first Brillouin zone. We construct a Bloch state by taking a coherent superposition of atomic orbitals, one centered at each Bravais lattice site R, weighted by the phase factor e to the ik.r. We further assume the orbitals on different sites are orthogonal, formally working in a Wannier basis, so the eigenvalue problem reduces to a standard matrix problem at each k. To see the mechanism cleanly, we begin with the simplest non-trivial case, a dimer, two identical atomic sites, I and j, each contributing one orbital. Two matrix elements characterize the Hamiltonian. The diagonal element, epsilon naught, is the on-site energy. The off-diagonal element, defined as -t, is the hopping amplitude. For S-like orbitals with no nodes between the sites, the lobes overlap with the same sign, and the kinetic energy contribution to this matrix element is negative. This is why T is conventionally taken positive for s-orbital tight binding. In the two-site basis, the Hamiltonian is a 2 by 2 matrix with epsilon naught on the diagonal and -t off-diagonal. Solving the secular equation gives two eigenvalues, E plus minus equals epsilon naught plus or minus t, with eigenvectors equal to the symmetric and antisymmetric combinations of the two orbitals, divided by root 2. The lower energy symmetric state is the bonding orbital, the higher energy antisymmetric state is the antibonding orbital. A single atomic level has split into two by an amount 2t. This level splitting, scaled to a macroscopic number of sites, is exactly what generates a finite width energy band. We now extend the construction to an infinite one-dimensional chain with lattice constant A, retaining hopping only between nearest neighbors. We act the Hamiltonian on the Bloch state, the sum over n of e to the ik and a times the orbital at site n. The on-site term contributes epsilon naught. The hopping term moves an electron from site n to sites n plus or minus 1, picking up phases e to the plus or minus ika, projecting onto a single site. The two phases combine via Euler's identity into a cosine. The result is the standard one-dimensional tight binding dispersion. E of k equals epsilon naught minus 2t cosine of ka. The discrete atomic level has been replaced by a continuum of allowed energies, indexed by the crystal momentum k. The first Brillouin zone runs from minus pi over a to plus pi over a, and within it the energy varies smoothly from a minimum of epsilon naught minus 2t at the zone center to a maximum of epsilon naught plus 2t at the zone boundary. The bandwidth is exactly 4t, set entirely by the hopping. Stronger overlap means larger t and a broader band, weaker overlap recovers the atomic limit. The same procedure generalizes to higher dimensions. On a two-dimensional square lattice, every site has four nearest neighbors, 2 along x, 2 along y. Each pair contributes an independent cosine, and the dispersion becomes E of k equals epsilon naught, minus 2t, times the quantity cosine kxa plus cosine kya. The energy is now a function on the two-dimensional Brillouin zone. At the zone center gamma, where kx and ky are both 0, both cosines equal 1, giving the band minimum at epsilon naught minus 4t. At the zone corner M, where kx and ky both equal pi over a, both cosines equal minus 1, giving the band maximum at epsilon naught plus 4t. At the zone edge midpoint x, where kx equals pi over a and ky equals 0, one cosine is -1 and the other is +1, the two cancel, and the energy is exactly epsilon naught. The x-point is therefore a saddle point of the dispersion, and saddles of this kind produce a logarithmic singularity in the density of states known as a Van Hove singularity, a feature relevant to instabilities in real square lattice materials. To extract the low-energy physics, we expand near the band minimum at the gamma point. For small ka, cosine ka is approximately 1 minus 1/2 ka squared. Substituting into the dispersion, the band edge becomes parabolic. Measuring energy relative to the minimum, E of k minus epsilon naught minus 2t, equals Ta squared k squared, in one dimension, with the same coefficient Ta squared multiplying the magnitude squared of k in two dimensions. Comparing this to the kinetic energy of a free particle, h bar squared k squared over 2m, we identify an effective mass. M star equals h bar squared divided by 2Ta squared. The quasiparticles near the band bottom propagate as if they were free particles, but with a renormalized mass set entirely by the lattice geometry and the hopping amplitude. A large hopping yields a wide band and a small effective mass, and the electrons are highly itinerant. A small hopping yields a narrow band and a heavy effective mass, and the system is pushed toward strong correlation. Effective mass is therefore not a property of the electron in vacuum, but an emergent feature of band formation, valid wherever the parabolic approximation near a band extremum holds. From a single hopping parameter on a one-dimensional chain, we have built a complete and predictive description of an electronic band. The same machinery, applied to other lattice geometries, generates the rest of nearest neighbor band structure. On the square lattice, the dispersion has a saddle point at the x-point, producing a logarithmic Van Hove singularity in the density of states. The triangular lattice has 6 nearest neighbors per site and yields a band that is asymmetric between its top and bottom, reflecting the lack of bipartite structure. The honeycomb lattice, with its 2-atom basis, is the lattice of graphene and gives rise to its Dirac cones. The Kagome lattice, built from corner-sharing triangles, produces a perfectly flat band by destructive interference. Each of these lattices is described by exactly the same tight binding framework we have just constructed. Only the geometry changes.